Welcome on this Petri tutorial from Symmetric Net to Symmetric Net with bags. This is the first session of this tutorial. Here are the outlines of the tutorial. So first of all, I will present you this morning an introduction. Then we will deal with syntax and semantics of symmetric nets. And we will discuss about symmetric nets and the verification of distributed systems. So let's start with informal introduction about symmetric nets. In fact, you already know place transition nets. Place transition nets, you know that you can have tokens in places. The token in places, in fact, they just represent the existence of a resource, and using constraints located on transitions, you can generate resources and consume other resources. In fact, it's a nice notation. It's very useful to model distributed systems. But you have some troubles when it deals with large systems. Let's imagine that you have, for example, a system with 10 clients and 5 servers. You will more likely be tempted to have repeated patterns for the clients, for the server. So very quickly, you get very complex Petri nets to handle. So let's have a deeper look on what you can do with that now. So when the Petri nets were invented, you have a first level. The first level here characterizes Petri nets where you can have a token that notifies the existence of a resource or no token. So basically, the tokens represent Boolean values. Then you have level 2. And level 2, the idea, it's place transition net. The idea is to have as many tokens as you want on your place. It means that basically you encode a sort of integer value. But if I have one process and a token per program counter, so it means that any occurrence of a process will generate an extra counter, then you still may have a problem because you cannot make a different distinction between one process and another. So it's a first step that is comfortable, but it's not enough. Then high-level Petri nets were introduced, and the high-level values carry a value, the tokens carry a value, and it can also carry composed value, so a sort of record-like data type, and it's quite comfortable because, for example, if you model a game where you have a given player, and the given player has that many gold pieces, that many copper pieces, etc., you can have a composed token that will hold together the identity of the player and the amount of gold pieces and copper pieces, etc., whatever he does carry out with him. So it's much more comfortable. The semantics is exactly the same, but the specification is much more compact and then much more easier to read. In fact, symmetric nets that were previously named well-formed net in the old literature in the 90s, they were renamed symmetric nets when the standardization process started. They were named symmetric nets because while we were doing a standard, people thought that the word well-formed would mean that other Petri nets are not well-formed. Some colleagues say this is true, but in fact, it was not nice for others. So it was renamed symmetric nets. They are a form of high-level nets with constraints on the way we will handle these data types that are carried out by tokens. Let's have a small example here, just to show what's the structure of a Petri net. So, as for all Petri nets, you have places here, and you have a transition here. But what you note is that every place has an extra information that is called the color domain of the place. And in fact, it denotes the type of values that will be held on tokens. And also, you have here annotations on arcs that are colored functions. It means that when I gather from this place a token, I will apply this color function, and the firing will depend on these color functions. And of course, it means that you also have a color domain for a transition. And in fact, intuitively, the color domain of this transition depends on the color domains you have on the input places and on the output places. It's a sort of Cartesian product, except if, of course, they are all the same colors, and also if you have connections between the values from this arc here and this arc here. So it means that these annotations allows you, when you do your modeling, to handle sorts of data types. Let's have a first example. So it's very close to the illustration I was giving you to show that it's much more compact to write. Here I model a process. So you see this process here, okay? And this process, you carry out some information. So these places, these three places, they have a color domain. The color domain is CL. CL is the identity of the process. And here you have a classical token, a classical place that only holds, we call them black tokens, traditional tokens, like for place transition. So what does it mean? It means that here in idle, I will have an initial marking here. This initial marking is here static functions. This static function called all, all applied to a color domain will generate one token per possible values in the color class. So it means that, for example, if my processes have identities that are a value in between 1 and 10, CL.all will generate token 1 plus token 2 plus token 3, etc., until token n. Here you have valuations on arcs, and the valuation on arcs here are just a variable. It means that, let's consider, for example, place weighting. It means the transition, T1. So it means that it will extract a token F. It's a variable, and it will extract this token from place idle, and it will generate the same token in place weighting. So here, the only function we have is the identity function. We will see later on this presentation that, of course, you have, even if they are limited, a quite large number of possibilities. Here, the example has been changed a little bit. In fact, we consider here that to have this process being executed, we need to use a resource. For example, a core. We must decide that this process will execute on a given core. So here, it's interesting because of that. Because if I consider transition T2, transition T2 takes one F from weighting, one G, it's hidden here, from rest, okay, and it will generate in busy a Cartesian product, so associating the process F with the resource G. And it means that here the operation is a Cartesian product, so I'm making this record associating. So when I fire transition T2, I can fire any process with any available core that is in res. And when I am executing the process, I know I have the actual association between a given process and a given core. So this is just an overview. The example is a little bit more sophisticated than the one I just presented 1 minute ago, 1 slide ago. And of course, everything that you have in traditional Petri nets, such as the initial marking. So here the initial marking is idle contains cl.all, and here res CLP, sorry, the class for process.all here, and CLR, the identity of resources here. Okay, so it means that using that you can represent your Petri nets, and you can, for example, if you look for a given situation in your net, say I want to see if core 4 can be associated to process 5, for example, and this will be a classic query that you can perform. If you want to do similar thing on place transition net, you must have one sub-Petri net per process. So it means that you will have, for example, if I have 10 process, I will have 10 times this, and then if I have 5 cores, I will have 5 times this place with all the possible connections between the process and the resource, and you will see that you will generate very quickly what we call internally a spaghetti net, so something that is almost unreadable. So, at this stage, you have an idea on colored Petri nets in general, and symmetric net. It's a very informal presentation just to give you the idea of, and later on we will have more detailed presentation, and in the next sequence we will go for more precise semantics.